All right, here we go. Section 4, forces due to multiple charges. Okay. All right. 3 charges are arranged on a line as shown. Each tick mark is 1 meter. Find the magnitude and direction of the net force on each of the charges. Okay, so really quickly, okay, I'm gonna. If you had me for Physics 1, then you may be familiar with this notation because I used it just a little bit last year. But I'm going to use it a lot more in E&M because it is more prevalent in E&M. Okay, if you see me say F21, this means the force of object 2 or charge 2 on object 1. Okay, so just understand that if I say that, that means this is what object or charge number 2 is doing to object or charge number 1. Okay, pretty straightforward. Okay, or at least I think. So we have 3 charges arranged in a line. Okay, I'm going to use different colors for each one so that we can make it all pretty. Okay, this is Q1. Okay, this is Q2, and this is Q3. Okay, so we've got all the charges on a line as shown. Each tick mark is 1 meter. Find the magnitude. Okay, so first off, right, let's take a look at charge 1. Okay, you're actually going to notice that this problem is actually going to get a lot easier as it goes. Okay, so first off, right, the force on Q1. So we need to figure out what force does 2 apply to 1 and what force does 3 apply to 1. So the force of 2 on 1 is going to be equal to, K Q1 Q2 over R squared, right? Okay, and then we would just plug everything in. 9 times 10 to the negative, or 9 times 10 to the ninth, okay? We need to convert all these from millicoulombs into coulombs. So all we got to do is just do, this would be -1 times 10 to the negative third. And then charge number 2 is 4 times 10 to the negative third. Okay. And then the distance between them, we count each tick mark, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 10 meters. So then we would do 10 meters squared. Okay. You would put that into your calculator, and you would actually end up getting a net force of 360 newtons. Or sorry, so 2 would apply a force of 360 newtons to 1. Now, here's the question. You notice I didn't put a sign there. It would be negative, okay, but it's actually less important to know the sign and more important to know the direction, okay? So what direction is 2 pulling or pushing 1? Well, notice that the signs are opposite on the charges, which means they're going to be attracted. So this one, Q1, is going to feel an attractive force towards Q2, okay? Okay, so F sub 2(1) is 360 newtons to the right, okay? Okay, now this is the 3 applies to 1. We're going to do the same thing, plug everything in. 9 times 10 to the ninth, okay? -1 times 10 to the negative third. And then the charge this time is now 2 millicoulombs, so it would be 2 times 10 to the negative third. And then the distance between them is a really long distance. 1, 2, so it's 10 to get to there, okay? 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, so it's 30 away. Okay, 30, not 32. Okay, 30. Okay, and you should end up getting about 20 newtons, and this is going to pull, again, to the right. Okay, this will also pull to the right because it's also opposite sign, right? Okay, so it's going to pull to the right. Okay, so the net force on charge number 1 is just going to be the sum of these two. And since they both pull in the same direction, you're just going to add them together, right? So it should end up being 380 newtons to the right. Okay, pretty straightforward. Nothing too crazy, right? We're still kind of chilling, right? Okay. The force on Q number 2 is going to be, we only need to solve for one of them here, and I'll show you why that is, okay? The force on Q2, okay, well, let's figure out the force that 3 applies to 2. So force of 3 on 2, okay, you would do this time KQ2 times Q3 over R squared. And if we plug all the numbers in, 9 times 10 to the 9th, okay? Q2 is 4 times 10 to the negative 3rd. Q3 is 2 times 10 to the negative 3rd, okay? We plug all that stuff in, and then we get our new distance, which in this case, so we know this is 10. So you could think of it like this. You could do like, oh, this is 10 away from 1, and then this was 30 away from 1, so the difference is 20. Or you can count. Either way is fine, okay? And you do all that stuff, you end up getting about 180 newtons to the left. And the reason it's to the left is because they're the same sign, right? Positive, positive, okay? So this is going to go this way, okay? Now, here's a fun fact. We don't need to do any more math, okay? We're done with math, okay? We're done with math. Sayonara, right? The force that 1 applies on 2 should be equal and opposite to the force that 2 applied on 1. Because again, they both are experiencing the same force. So the force that 2 applied on 1 was 360 to the right. So the force that 1 applies on 2 should be 360, but to the left. Okay, you with me so far? I don't know why I'm saying that like you're right here, right? Okay. And finally, the net force on 2, you're just going to add these up because they both go in the same direction, right? I forgot to draw my arrow on the diagram up here, right? Okay. You're going to add these up because they go in the same direction. 180 plus 360, okay, should give you 540 newtons to the left. Pretty straightforward, right? Beautiful. Okay. The force on Q3. You don't have to do any math to solve this anymore. Okay? We just need to figure out the force that 1 applies on 3, which we already did, but instead of being 20 newtons to the right, it's going to be 20 newtons to the left. Okay? So I'm going to go back up here and draw the arrow to the left because that's where it pushes. We've already figured out the force on 2 and, from 2, right? Okay? It's 360 to the right. Oh, sorry. It's 20 newtons to the right. Okay? Or sorry, no, over here. 180 newtons to the left. So the force on 3 is 180 newtons, but to the right this time. Okay? And that's because, again, they're repulsing each other. Okay? So the net force on 3, well, because they're in opposite directions now, we actually need to subtract them. Okay? That should give us 160 newtons, and the net force will go to the right because the rightward force is greater. Okay? Incredible, right? Okay. Let's take a look at this example right here. Not everything is in one dimension, unfortunately. Okay? Not everything is in one dimension. Most things, in fact, are in 2 dimensions. Okay? So this is going to be an example that is 2-dimensional, okay? Where you can have charges move up, down, left, right. They can move all over the place, right? But this is an example, okay? Find the net force on Q0. Express the force as both components and as magnitude and direction, okay? Well, first off, you should notice that we're trying to find the force on Q0 or Q0. I guess I'll call it Q0. It doesn't really matter, right? Q0 is a positive charge, okay? Q1 is negative, and Q2 is positive, okay? Okay, now when you have this, okay, you need to figure out which charges are pulling and which charges are pushing on Q0, right? Well, you'll notice that Q0 and Q1 have an attractive force because they are opposite signs, right? So you have a force pointing to the left. Okay? This is the force of charge 1. Okay? The force of charge 2, it's same sign, so it's going to be repulsive. Okay? And that's the force of 2. And the net force is then going to be the resultant of these 2 vectors, which is just going to point up and to the left. Okay, so in order for us to solve this, we would have to use a little bit of Pythagorean theorem, okay, but not quite yet, right? Let's figure out the force that 1 applies to it. Okay, and again, I encourage you to try these on your own, right? Instead of just watching this all the way through. K, Q1, Q2. I guess it should be, sorry, Q naught and Q1, just to make the notation more consistent with the problem, right? Okay, over the distance between the two squared. Okay, we'll call that R1. Well, we plug everything in, 9 times 10 to the 9th, okay? Q naught has a charge of positive 1 millicoulomb, 1 times 10 to the negative 3rd. Q1 has a charge of negative 12 millicoulombs, negative 12 times 10 to the negative 3rd, okay? And then the distance between the two is 1, 2, 3, okay? 3 squared. And you would put that into your calculator and you would end up getting 12,000 newtons to the left. Okay? Okay, for the force of 2, K Q naught times Q2 over the distance between naught and 2, okay? Well, we just plug everything in, right? You can get it right from the problem. 9 times 10 to the 9th, 1 times 10 to the negative 3rd, and then finally we have 16, just positive 16 times 10 to the negative 3rd, okay? And the distance between the two is 1, 2, 3, 4, okay? And you punch that into your calculator, you end up getting about 9,000 newtons going up, okay? So then you would need to figure out the resultant of the vectors, which is pretty straightforward. All you got to do is use the Pythagorean theorem, okay? So you'd use the net force is equal to root 12,000 squared plus 9,000 squared, and you would end up getting 15,000 newtons, okay? Now we still need to figure out the angle because we need to figure out the direction. Now, the angle, right? We want to figure out, you can either figure out this angle right here, but I think the safer bet is going to be if you actually solve for this angle right here. Okay, the one in pink, okay? It's actually probably going to be better if you solve for that angle instead of going for the one in red, okay? The way that we can do this is that if we have this angle, we know what the opposite and the adjacent angle is, so we would use the tangent function, okay? So it would be tangent theta is equal to opposite, which would be F2, so 9,000, over adjacent, which is 12,000. Okay. Oh, wait a minute real quickly. 9,000 over 12,000, can that simplify any further? Yeah, it can. We can get tangent theta equals 3/4, right? That makes sense. Oh, and tangent theta 3/4. Well, I'm built different. You might not be. So I know it off the top of my head. It's 37 degrees. You might not, though, but you should know it because it's cool, right? Okay, so if you do on your formula sheet, you can tell I'm losing my mind because I'm starting to show my actual classroom personality right now, okay? If you get out your formula sheet, you can actually see that they provide you trigonometric functions, okay? Okay, so tangent of theta equals these things in the table right here, right? And then the parts on the top is what theta is. Okay, so what theta gives me 3/4? Oh, there's 3/4. Oh, 37 degrees. Oh, beautiful. How wonderful. Thank you, Mr. Mitchell. Okay. So all you got to do is just then you use that table to figure it out. You could plug it into your calculator, but that takes away precious time. You would have to do inverse tangent, and you know, when you have to find inverse tangent on your calculator, people start to cry, right? So I'm not going to make you do that. You can just memorize it, okay? You're big kids now. You can memorize values on the table, okay? Or you can just know how to find it on there. So it should be about 37 degrees, okay? Now that is giving you this right here. That gives you that angle right there. If you wanted to get the angle in pink, you would just have to do 180 degrees minus the 37 degrees, and you would end up getting 143 degrees. So I would report this as 15,000 newtons at 143 43 degrees. You probably can do it the other way and say 37 degrees north of never eat soggy watermelon, north of west. But I would say just to be on the safe side and do this with respect to where 0 would be on the unit circle, okay? I know, you're freaking out now because I said unit circle and you're like, oh my gosh, what the heck? Okay, this is really quick example, right? Draw the force F sub A that charge A exerts on Q. Draw the force F sub B that charge B exerts on Q. Then draw a vector F for the net force on Q. Then write an expression for the magnitude of the force Q on the other two charges Q. Okay, so if we take, for example, right, we have a positive charge at the origin. We have charges A, which is positive, and B is negative. So you're going to notice that the charge of A, okay, the charge from A is going to apply a repulsive force going down. Okay. Okay, I really need to make sure you see that blue line. And then B is going to apply attractive force going to the right. Okay. Okay. Now, to figure out the net charge, or the net force, right? The net force would go down and to the right. Okay. The net force would go down and to the right. Okay. We would need to take the forces of each individual charge applies, right? So what we could do, here is if we have, oh, sorry, wait, let me back up for a second. Did I miss something here? So it should be draw a vector F for the net force. Finally, write an expression. Oh, magnitude of the force on Q due to the other two charges Q. Well, you should notice that there is, oh sorry, this is F sub A, I forgot to label these, right? F sub A and F sub B, okay? What you should notice, okay, is that the charge that A exerts, right, should be K big Q little q over R squared, okay? And then you should see also that F sub B is also K big Q little q R squared. Now here's the difference, right? The charges are same in magnitude, but opposite in direction, right? And I guess I should be more specific, and instead of labeling it with R, say D instead. But as long as you get the point that D is representing R here, it's not that big of a deal, okay? Okay. Oh my gosh, and if I erased it just to write R again. Am I stupid? Okay. Okay, there you go, right? So then what you would do is you would then be, right, you have the force of A, the force of B. Well, then to find the net force, you need the Pythagorean theorem. So what you would end up doing is you would plug these into the Pythagorean theorem. You would get K big Q little q over D squared, the whole thing squared, plus K big Q little q D squared, whole thing squared, and set that equal to, you would set that equal to, if you added that, right, you would get another quantity that is squared, and you would have to take the square root to figure out what it is. Well, if you take these two are the same expression. This is the same thing as saying 2, let me put it in like big print brackets here, okay? 2 K little q big Q over D squared, okay? And that whole thing is squared, okay? And that makes sense because, right, these two expressions are identical to each other, so you're just taking one expression plus the same expression, so it's 2 times that expression, right? Okay. Let me actually, I think I wrote this like super complicatedly. It should actually be, I really like messed up here on the, because I was trying to be all fancy with my brackets and stuff, right? This is just the same thing as saying 2 K big Q little q over D squared, and that part's squared, okay? I guess I didn't really need the brackets right there. I was just trying to be weird. Okay, But you're going to notice, right, the Pythagorean theorem gives you a result that's squared, and you actually have to take the square root to get what you want. So then you would take the square root of this part right here, okay? And when you take the square root of that, you're going to end up with a new value, which is equivalent to, you would notice, right, that root 2 is going to be in here, but this part right here is squared. We can actually pull that out of the square root. So it should actually be root 2 times k q over d squared, okay? And the square just gets canceled out by the square root, okay? All right, pretty solid, right? All right, Gaslight, Girl Boss, Gatekeep. Have fun.